So today I'll focus more on vectors and the relevant application. Multivariate optimization, this last quarter we showed, we have explained and shared with some of you about how to do multivariate optimization. So today I think I skip a little bit on this part. If those of you really find, hey, this is something I really want to hear, hopefully next month we'll come out a special topic just for address multivariate optimization. Now, let's straight dive into these issues about matrices and vectors. And in Wolfram programming language, if you are using it one way or another, or you're new today, not to worry. We using matrix and vectors interchangeably, more or less, actually in Wolfram Mathematica. So now, if you see here on the screen, I define a simple matrix 1, which is 1, 2, C, matrix B, which is ABC. So in this case, you want to perform normal operators, so I can just say, hey, A matrix 1 minus matrix B matrix 1, just something like that. So of course you want to do some scalar multiplication. This is how it goes. Yeah. So the simple thing is that I do not want you to go through too much on, like say, I only spend about 5% on this, because in Wolfram Mathematica there's a palette available to help to construct vectors and matrices and perform all the operations very easily. So we will leave it to you how to actually use those calculators, either actually built in with Wolfram language or somewhere you get a website or some of the calculator you have had. But just let you know that this usually those actually, especially those actually seeing Wolfram for the first time, they have some rough idea actually how the interface works. So if I do a dot scalar product, this is how it works like that. If for instance, if I have now matrix the 2 by 2 and doing the scalar product on now 2 by 2, this is what I get. Now, if I want to do a cross product, very simple. It is like something you see in normal textbooks, and you have a clause here. Of course, that you say, hey, how they come across it? Is that X? No, it's not X, because in Wolfram Mathematica, everything is symbolic. So you have to define some of the syntax a little bit correctly. So I have it type, say this cross product. But of course, you say, hey, how do I remember all those syntax? Not the way, like I say, there's a lot of visit, there's a lot of automation built in when you try and construct your syntax along the way. Actually, it'll try and guide you. I'm showing you here is like more like programmer approach. Sometimes I just type in some syntax or some short form quickly so I can get a result that I wanted. Now, if I further take a look some other important and fundamental functions that how we can handle certain matrices. Now, in this case here, for instance, there are using back the previous examples like A. Now I call it A matrix 2 and A matrix B matrix 2. There's another 2 by 2 matrix. If I do something like that, inside Wolfram Mathematica, is in either vectors or matrix, you use curly bracket to describe your element accordingly. So in Wolfram language, we call list. So of course, we as users, we have differentiates whether it's vectors, you use for purpose vectors or matrix on your own. And of course, in terms of data analytics, you use matrix a lot. And when it comes to engineering and some science application, you use vectors a lot. So they have some functions that designated more actually for the engineering use in terms of vectors, visualization, some of matrix manipulation. So today we will focus more a little bit on the vectors visualization. So in this case, assuming I construct a simple vectors, which is 2 by 2 here, yeah. So if I want to get a determinants, let's say assuming this now matrix right now, I just want to get a determinants, which is exactly the same thing as like A mac 2, B mac 2s, but I instead of keying here A mac 2 and B mac 2, I just copy and paste the previous output here inside here to get the determinants that I want in terms of matrix. So this determinants come up directly for us. Now, secondly, let's say I want to get an inverse. The same simple is this inverse. So now, in the ways that Wolfram handled coding, actually is quite easy. Is that if we type along the way, sometimes you spend our convenience. Like this one, just quick note, because along the way, sometimes I will do something like this, do a double backslash, and it actually resulting is same thing. So inside here, meaning sometimes I want to put function name in front with a square bracket. Sometimes just to quick show how it works, I'll put double slash in the function head behind. So actually give me the same thing. This is a little bit syntax thing, but the reason I'm telling you is along the example I show you later, sometimes I'll use this thing interchangeably. So you will not get confused. So what I'm trying to do is that like divider two types. No, it's not divider. It's simply a short form to put function that behind or some of the formulas that we have had. Now, if I want to put a norm, that's normal vectors field, and you give us normal output in terms of vectors. Let's say I want a projections, yeah. In these two vectors elements, these projections, if I want to see the vectors angle, so on and so forth. Of course, there's amples or others and syntaxes, the fundamental ones, perform all the operation you want. So, but today we are not going to focus on this area. Just will we quickly move on. Just let you know that you want to use as normal calculators, no issue. This is always available for you. Now, if we say, hey, I'm just someone actually want to get started. I don't want to do teaching and research. I just want to quickly for my own benefit. I just want to get some result quickly. How do I do that? So for those actually seeing Wolfram before or used before, you know actually how intelligent it is, especially you have actually kind of AI smart syntax built in, auto understand the human verbal language. For instance, I'm not sure, I know you probably have tried before durian with rice, but let's say there's some masala who are interested, say, hey, I want to combine durian with bread. Is it possible? So if you simply type in something like that inside Wolfram Mathematica, and in fact, try to make sense what we are trying to do. In this case, you say, if you eat durian and bread together, this is how much calorie you're going to get from 50 grams of bread and plus 140 grams of durian. This is how the nutrition table that will come out, calorie, carbohydrate, all the things that actually doing tabulated way. So in Wolfram Mathematica, later in some example, when I'm trying to show some vector field, and I'm making use of some of the curated data that pull out from those knowledge engine. So for instance here, you say I'm new to actually vectors. I just want to actually make sense. How do I do cross product 1, 2, 3, 4, 5, 6? It was simple. Of course, you can make more complicated if you want to. But today, I say I only want to see how many visualize it. Actually, what does this mean? Actually, cross product 1, 2, 3, and 4, 5, 6. Oh, this cross product actually is like using right hand rule. Yeah, I have this 1, 2, 3, probably this 1, 2, 3, and a 4, 5, 6. And something perpendicular, cross product is perpendicular to both of them. This is a right hand rule I'm using. Then can start explaining or give you yourself a reminder. How does it work? Now, you also have some other thing that, for instance, interesting thing, how does it come out result? And can you show me step by step? This is wonderful. If you especially have a more complicated cross product, you want to somehow show in the class actually how it works, then this one shows step by step how entire cross product is being carried out. Accordingly, of course, getting big lengthy, but more lengthy is actually is more detailed, actually is helpful for our own understanding. Now, enough talking about this curated language, curated data, tabulated data using Wolfram knowledge base. So you can try it out on your own if you want to. Now let's go straight to the vectors field plotting. I think you're using vectors, you will be very concerned and use a lot about vector field plottings and how good you can visualize it. For instance, if I have a formula equations like that, you see this is like syntax like I have y squared divided by 2 minus by x squared divided by 2. So in this case, let's say I want to find out, illustrate what's the direction and rate of fastest increase. These are three-dimensional graph, yeah. But I want to see this three-dimensional graph. I want to make it to be a direction plot, meaning that I want to see how rapidly the change of rate is happening on this three-dimensional graph. Of course, if you want to see how the three-dimensional graph look like, it's very, very simple. You just say, hey, I want block 3D. Block 3D or what? I want block 3D or this thing. So you say, hey, yes, this is functions. Yeah, M, F01 is my functions. I want block 3D when X range from -3 to 3 and Y range from -3 to 3. So in this case, you show you a three-dimensionals and plot things right away. And this is how it looks like. But in this case, let's say I want to have a contour block. Yeah, I want to have a top view on an XY plane. So in this case, I just create a contour block. based on same equations that I just have used above, my f01. Same thing for a range of -3 to 3 and y is -3 to 3. I want to have a legends which is coming up for me automatically. Say, hey Peter, what this legend is? Yeah, inside every function here in Wolfram Mathematica, like I mentioned before, is have a lot of automation of visa built in. You can choose what to do with that. But as simple as sometimes that we just say, hey, I don't want to know anything else. I just only interested in knowing what's a contour plot. But along the way, sometimes that you want to visualize more and more. You say, hey, is there a way for me to see what's a label? I want to put a label. I want to see there's a legends telling me what's the colors, values all about in different areas. So in this case, for instance, even though when I mouse over it, you show me all the value that's associated with each contour, but I just want to show it more and more, something like how I will actually show in Excel spreadsheet in a chart form. Trust me, in Wolfram Mathematica, you can program dynamically. Actually, you can come on much more domestically than you could achieve in Excel spreadsheet. Yes, but today we are not talking about how to make it more beautiful. I'll just let you know from contour to plot. Now, the next thing is I say, hey, I want to visualize directional plot of these vectors. So in order to do this, is very simple. I just get a gradient of my f01. What does mean gradient? Simply is a partial derivative in terms of x and y above these functions. So in this case, you get the change of the rate on this 3D graph. So in this case, if you get a partial derivative in terms of x and y on this function, simply I get minus x and y. So if I get minus x and y, now I can start plotting my vector field. Yeah, if I know what's the range of change, that will be the beginning how I can start with the vector field. So to get my vector field visualized accordingly, it's very simple. So again, same thing. I want to change it with I want to remain as range of x from -3 to 3, y is -3 to 3, exactly on same dimension. But in this case here, say a block 3D. I say, hey, now I want a vector block of these functions, which is have a gradient. That means partial derivative for x and y. So in this case, actually show me a directional flow of this vector field accordingly with the legends on the right-hand side, showing you what's the magnitudes of which vectors. So in this case, of course, that like I say, there could be many other domestic things you can put in accordingly. But again, I just quickly show you some, so you do not have to keep in mind. Just let you know what are achievable. These are actually hundreds of examples how you can achieve different things. For instance, you say, hey, I just want the vector points to be something like finer than previously. So I put vector point fine. So what in this case I say the scaling one, can you help me do some scaling? So this one's slightly smaller, you might not be able to see, but let me take away this fine, it'll be easier. So you want the magnitude itself to be graphically show accordingly is that the bigger the magnitude is, to be longer the arrow is. Like this one is lesser the magnitude is, the smaller the arrow. So this is called vector scaling. But of course, you say, hey, Peter, in this case, I want to have, like, for instance, can you show me a density? I want to see the density instead. Of course, there are many ways, not just density. We want to visualize it. The density is just one small things, and probably want to use for our own satisfaction. But the next thing is sometimes when you come in classroom, you say, hey, now I'm able to show vector field, but I want to see how actually this whole thing works in animations, easier to see, because you see there's a lot of websites when people putting some of the teaching material. These days people cannot run away putting a movie. So people are very pampered this day. You not just want to, well, if you're researchers and you're scientists and mathematicians, you don't really actually concern much about the animation. But sometimes when it comes to teachings, that you say, hey, animations actually does explain better than the statics picture sometimes. So in this case, the same thing. Now, to do animation, I'll put the same dimension, x from -3 to 3, y from -3 to 3. Same thing is vector plot. The only thing I have to do is I put in animate. So animate meaning is that animate what? I put in 2 more extra parameters arbitrarily in front of x and y, means that minus ax and now it's by. So a will actually will change from -10 to 10, while B, these are parameters, arbitrary parameters are changed from -10 to 10. So in this case, I put animate. Animate is not my most popular choices. I tell you why later. So in fact, animate, when you run it, of course, you can use these buttons to actually toggle it accordingly. But animate would not actually allow you to key in some of the value that you want, specifically to show the graphic accordingly. So animate sometimes is a quick way of showing things how actually run your animations. I'll show you another actually much more robust actually syntax to help you to visualize in a very interactive way later. So now, in other animations, let me just delete this thing so you stop consuming so much of my memory. So the next thing is, let's say I want to do visualization slightly more. So what could we do here? So if I want to do something like string block, of course, we have this vector field block. A lot of times, sometimes I say, hey, could I actually look at a string, the string flow of this vector field? So in this case, similarly, everything remains the same. The only thing is I add additional things called mesh. Yeah, let me take out mesh first to keep the syntax simple. So instead of vector block, I change it to string block. Same function, mg01. Yeah, this is after performing gradient on the functions my f01. So now the string block will look something like that. Yeah. So actually, with all the lines connecting to one another, you see a string coming up. But of course, in that case, I say, hey, I want to. Can you help me to look at? I want to have some mesh accordingly. So actually, have better reference my own. So let me see. Here we go. Now, I just come up with 5 mesh. I just say specify that the mesh will be in red color in thick one. But let's say if I want to show entire the mesh instead of the 5 mesh, and then see how it looks like. Yeah, it looks something like that. Yeah, so it's just another way of illustrating the vector fields that we just actually define. So now again, when do this, if we can animate vector block, by all means, I think some of you already crossed some mind. Hey, could I actually animate this string block? Yeah, those are domestic. I don't want to spend too much time here, but just let you know, in terms of visualization, it's a symbolic package like Wolfram Mathematica, who first designed symbolic package. It's very powerful in handling a lot of visualization. So you say, hey, Peter, already done a lot of project Python R. No issue. So you see, one thing here, I think hopefully we will come out sessions available for particular how to talk about integrating with Python R. Let's say I turn off this screen environment and switch one slideshow to working, meaning that now, let's say I want to key in some additional thing here, for instance, when talking about doing vector field transformation. In front here, you see I have Wolfram language input, the default one, free-form input, and also have external language input. If I have external language input, if I click on this one, the next thing is they'll come out dialog box to say, hey, which one are you trying to input? You see, this one come out a little bit called Python. You can actually insert the Python actually coding inside. Some other actually use tools like language we use a lot as open source, like including R. So if you can run entire R coding here and just pass out the output directly into Wolfram coding, whatever you have been developing, you can do actually pre-processing, post-processing of visualization. Just let you know that the whole integration actually is there. You do not have the concern, hey, when I've done something like in Python, I want to make use some useful features from Mathematica, I had to rewrite everything and go through a middleware. No such thing this day, at least not for Wolfram Mathematica. Now, vector field transformation, we will not spend too much time. There's a whole bunch of examples available, and if you want to, let's say I want to change from my Cartesian system to polar system. So I don't know, I will not come out any typical example why I'm doing that, and just let you know that the transform field is very simple. You can transfer to some of the system like default Cartesians, or you can change interchangeably, let's say from polar to Cartesians. Most of the time we do it in reverse with some other systems that want to change the Cartesians one. So in this case, the two elements we're dealing with is minor x and y. So we say these x and y parameters, I will also associate with the polar systems, X will associate with R and Y associate with theta. So transform field just immediately will come up for you, the transform field accordingly. Of course, how do we do visualization? The pretty much the same approach in the following way. Now, we quickly go through several other examples. So we have some time actually to go through some interesting example that we have had. So in this case here, what if now in our vector field, we have defined functions. We want to plot a vectors field over a specific region of or domain. In this case, there's a simple example here. For instance, now to keep things simple, I just take away this thing. Yeah, I take away this thing, so the coding will not look like so complex. So the vector block I'm using still remain the same as previously, minus x and I change a little bit. Is previously is minus x and y. Now I'm minus x and minus y. X from -3 to 3 and y range from -3 to 3. I have region function like this. I say, hey, I want to be x squared plus y squared will be bigger and equal to 1 and lesser than equal to 9. I want these things actually fall over these specific regions that I just refined. So how does it look like? It will look something like that. Yeah, and just something like a big donut actually looking from top view when all the vectors pointing inward. In this case, I take away all the legends, things like that. So of course, if you say, hey, I want to see some of the legends and some of the colors and all those visualization. Of course, this, like I say, there's a many way of doing that. So just actually you can do it on pleasures. Another thing is another thing is, let's say I want to specify over a domain. How do I do that? Yeah, actually it's concept sake, but in this case here, instead of equations defined as functions, now I'm using this as domain. So the domain here, for instance, I have to define my domain first. So my domain, I define a user variable name I call DML, and this thing is a particular functions inside Wolfram Mathematica to define a certain shape. Now this shape with some XY coordinate 4 points. Yeah, it's a polygon. Yeah, it's a polygon. Yeah, it's an arbitrary shape. So in this case, the polygon itself with this x4 coordinates, it looks something like that. So this particular domain I have defined. So I can define a domain using some of the graphic functions available inside Wolfram Mathematica. So with the XY coordinate, plotting it accordingly. So the next thing is same thing. I'm using this thing. I'm using the symbols calling it the tail system. This one actually have to satisfy this domain. So in this case, the vector block itself still the same, minus x minus y. Of course, I do not have specified range anymore. Previously, I say from -10 to 10 and minus, and is it minus 10? Oh, -3 to 3 and -3 to 3. No, I do not have the tau system anymore. I say I want a vector block that actually fall into this polygon, which the 4 coordinates I just previously defined. So in this case, for instance, again, I say, I want to actually copy and paste this whole thing, the PowerPoint, Microsoft Word, whatever actually reports I've had actually, or in the classroom, you can add in more complex things you want accordingly if you want to. Now, let's quickly go to the next thing. So we will cover actually the interesting part later on with some applications. Now, in this case, you say, hey, Peter, what if I have a whole bunch of vectors kept in the Excel spreadsheet? I do not even have equation defined for that. How do I do that? In this actually class here, I do not want to show you an Excel spreadsheet, and sometimes I think I switch between screen. When you're listening to me about half an hour, you could probably lose track about what I'm trying to do in terms of doing importing a lot of data here and there. So I simply create a random data. Yeah, this is some random data I'm trying to create here. So what I'm doing here is I create minus xy. I create a minus xy based on this function. X will actually range from -3 to 3 and step with a step of 0.2. That means that you'll go to -3, -2.8, -2.6, all the way to 3. Same thing. This is the y will be range from -3, -2.8, -2.6, -2.4, be a step of 0.2. So I create actually a table with the range -3 to 3, while actually going this how many is, I think altogether 30 by 30. So let me see how big the matrix is. See, I'm doing right now double backslash. Now I try to do additional one functions. So this is one huge matrix here. Yeah, I think 60 by 60. Now, if I take away this thing, so I go back to original form, this is how my vector 01 will look like. Assuming I'm taking this data somewhere from Excel spreadsheet or just like key in very faithfully in the system. The next thing is, instead of using a vector plot, in this case, we are using the raw data rather than the function. So the system will interpolate for us a few data with a set of vectors that we just actually define inside my vector 01. So actually, when it comes to defining few vectors, you have a choice to define a function accordingly, or you could actually faithfully key in or import the set of vectors from somewhere using list vector plot. Of course, after you're done list vector plot, you can do a 3D plot if you want to using the same method. Yeah. Also, we can do a list string plot accordingly, so and so forth. Or logically, you know actually what will follow actually. So we will not cover this list string plot, and those whatever we can achieve with vector plot, you all can achieve with the list vector plot accordingly. So next thing is that now we just, of course, when vectors are being used extensively in engineering and science, so we can run away by showing the first example here using is physics. That is a very classical example. How do we actually plot vector fields in terms of electric field about some point charges? So in this case here, of course, I define a norm here. Yeah, I try to put a norm for formula down here, denominators. So again, in this here, x I'll range from, I also simply put between -5 and 5, y is between -5 and 5. So if I vector plot this electric field, yeah, assuming these are two actually point chart actually available, this is how actually they interact to one another from the electric fields when these two point charts are actually next to one another. But you say, hey, Peterson, what if actually I have some distance chain between these two different point charges? Yeah, of course, you probably thought, oh, okay, Peter, you can animate, you could do animation just now, so you probably can do the same thing. But like I told you just now, we're going to do something much more intelligent than animations. So I think those were used before, though. From Mathematica, one way to another, you know how powerful it is actually using manipulate. So in this case, let's say I want to make Q1 so that you actually make some distant change or distance between these 2 point charts, Q2 and Q1, these two user-defined parameters. I want to actually able to interactively chain it. So then I'll able to see on the fields actually what is going on. Yeah, visually. So in this case here now, I just say, hey, Q1, actually I want it able to interactively change between -3 to 3 and Q2 -3 to 3. So now the graphic here is still the same down there, but the moment I run it, actually it come out with now scroll bar here. Yeah, scroll. I can toggle accordingly. Now, if I to have specific value, for instance, I want this thing to be -1 to be exact. Yeah, so I can put a -1, so I stay -1. You see, now this one slightly similar to animation, but actually have more power control for you, allows you to actually key in any specific value if you want to. And of course, unlike animation, if you want to put in more tabs, for instance, I don't want to show the point charts, the electricity field, I want to show some other like force field that involved in between. I can actually create multiple tabs in here. But today, we are not talking about how to create interactions in Wolfram Mathematica and visualization. So if those are interested, and you can always check out how do I make use of manipulate function in such a powerful, robust way. Now, second example, okay, again, a simple thing, classical things that you always like, you probably have taught it your students in PM. Now, anyhow, we use it as an example. That is a simple pendulum swing. So using these equations, let's say assuming it's a frictionless, yeah, I want this thing theta velocity to satisfy this these vectors accordingly. So the only thing is I have to define is now theta and v. And of course, there's some other things that those are actually optional. You don't have to put inside here. But let's just take it out, see what I do. So a simple function defined like that. Now it's coming out this very nicely. So, and I say, hey, some additional domestic thing to behind. I want a vector point to be slightly mixed in 24. Yeah, so make it slightly to be finer. Yes, so it show like that. So again, you say, hey, I want to make some animation here and there for the analysis. Yes, by all means. Yeah, I want to show the density, vector density plot, and so on and so forth. Now, the next thing is, of course, showing 2D. Then you may be thinking, hey, how do I do 3D? Now, 3D is nothing actually fancy. So for instance here, I have a field here, another field here, the functions x squared minus y squared minus z. Yeah, is x, y, z actually three dimension here. So in this case, let's say I just change to traditional form, so it looks like something nicer, something looks like that. Now, if I want to change it back to something like computer form, yeah, this normal input form, this is how it looks like. So in this case, here's a simple thing. These three-dimensional R3, yeah, R3, this scalar field, yeah, I want to get a gradient. That means partial derivative into x and y and z. So in this case here, these gradients, they give me the vector field. Yeah, the vector field for this R3, it become 2x minus 2y minus 1, which is partial derivative for x and y and z. For the functions. Now, same thing. After you get a vector field, you just take this thing, putting down here 2x, 2y, and minus 1. Yeah, accordingly, the vector field, because I define this vector field here. Yeah, this vector field, I get a gradient. I just put that down here. Yeah, of course, I can get this result directly instead of putting in the user-defined function. It's the same way. Now, of course, if you want to do a procedural programming, you can actually put in here SQ line by line as it is, as logical as it is. Now, if I put it back to vector field, this variable, so I want to plot this x range from -2 to 1, from -2 to 2. Same thing is z from -2 and 2, and now this is how it looks like in 3D vector field. Yeah, just very straightforward. It's nothing fancy about. Of course, if you want to do something slightly more for further analysis, same thing. Say, hey, I want this thing to over user-defined functions, which this x squared minus y squared minus z, I want it to remain actually in the between -0, 1 to 1. Let me change to something like textbook format. Yeah. Now, in this case here, down here, now what you have to do is this vector field. Yeah, same thing as above, and of course there's some other things like vector points. I can just take it out to make it simple, make it less messy. Again, same thing. Region function here. I say this one is subject to the function x and y and z, where x and y and z. I want the system to make sure before I plot this thing, vector plot, I want the system actually to evaluate for me to make sure the original function actually comply to these regions -0, 1 and less than equal to 0, 1. So in this case here, now actually these two things are same. Yeah. Here we go. Now it probably say, hey, Peter, what is evaluate? Actually, it doesn't matter. It just tell that which one actually should be calculated first. If I don't put this thing here, it still work, but the whole computation be actually less efficient. It take more time. But I just want to make sure this thing always get evaluate first the region functions, then only I plot the 3D vector. So this one, the whole computation be more efficient. Now, to make this visualization better, I just make the vector points to adjust to something that we visually can see better. So vector point equal to 25. You probably will ask me why 25? Yeah, I tried the arrow. I'm not sure which one actually best come out with visualizations. So sometimes that's what we do. Yeah. So when computed to be small enough, it looks like, hey, this one actually fairly good enough for me to visualize accordingly. Now, this whole vector 3D field actually will comply to my original equations, which is between -1 to 0, 1. Now, let me try to this whole thing actually consuming my computer's memory a little bit. Let me see if I can just delete these things away so we can keep on moving. Yeah, here we go. Yeah, let me see. Yeah, still running. Give me a minute. Okay, here we go. Sometimes the system when doing this thing, the reason actually this is whole thing is keep on evaluating things along the way. So it actually been doing a lot of computations crazily behind. So occasionally when you run Wolfram Mathematica, you find actually, especially you try to do presentation, you have a lot of example actually opening in background, and you probably want to kill the kernel and only the run the one you want to show. So now, another thing is before we actually conclude with some real life example, and we say, hey, how do I deal with complex imaginary during unit 1? Oh, it's simple. Yeah, just a functional complex vector block. And for instance, using the case example here is z squared. Now I say the z is actually from -3 to -3i, the imaginary unit 1 to 3 plus 3 imaginary unit 1. So in this case, then now it will give me a complex vector plot accordingly. There's a lot more example, yeah. So, but actually, take a look. Now, in fact, I'll overrun the time a little bit. Now it's 41. I hope you don't mind stay for 10 more minutes then, and I will show you some. Because in this case, showing this thing, then you come to appreciate how this thing will come vectors in Wolfram Mathematica. The whole design of the engine actually can put the real use in such a powerful way to resolve some of the actually real life example. Of course, I can take as an example from in terms of basic biologies, chemistries, but I think to make it really making sense to everyone. So I think weather is something that we have to live with every day. So I always take this weather to actually some of the knowledge-based curated data as an example. This one will show as a good example. For instance, I want to take a current wind data in what we have here. In this case, like for instance, in Wolfram Mathematica, if you want to get some live data, there's a lot actually library available, and it's all free for you. So like those attend our session before, you know, sometimes I've been complaining about how painful it is actually to get some of the reliable data from some of the public archives, especially Malaysia. Yeah, you all agree with what I say. So like, if you want to get wind data, sometimes you go to the public website and really don't know where to look. Yeah, so, and not to mention you get a so-called repository you can actually directly connect it to your system for direct consumption. And let's say I put this wind direction data now, you're checking out my IP address right now, also knowing that what time it is now I'm assessing. So it's giving me now the wind direction I have here in Glen is where I'm residing right now, is where my IP address is. So let's say if we want to get a wind direction data, specifically on this day, 1st January this year, and Malaysia actually, like any other country in the world, they have this comply to some of the data repository internationally. That Malaysia have about, I think about 7 or 8 weather stations. They have been submitting data quite faithfully, but of course sometimes they do miss some data certain day. I noticed in 2020, 1st January, all the data are there. Especially on every day, they are collecting wind data every 1 hour. So we have actually new wind data updated on particular specific location in Malaysia every 1 hour live. But what I want the system to do here is, I say Subang Jaya, I want to get data from 2020, 1st January until now. You can get to past 30 years if you want to past 40 years. So the data I collect every day, 24 points per day. In the past few months, it altogether have 4,900, nearly 5,000 data points available. So of course that today we are not talking about statistics, but before I need to show you a little bit on this so that later on we come to vectors. Now in this case, that we are seeing that if I put a histogram, yeah, in this case I want to put into 20 strips with the probabilistic density functions. I want to show in terms of angular degree of the wind direction in Subang Jaya. So it's showing me that most of the time the wind is blowing like between 140 to 170 degree in terms of direction in Subang Jaya, and also between 300 320 in Subang Jaya. So we know the angular degrees right now in terms of histogram, but sometimes we want to visualize it and say, hey, I want to visualize it. How does it work? Okay. So now, this is a big chunk of function here, not to worry. So it actually just simply converting the looks inside the 360 degrees, and something like that. So actually, I can see much clearer. So what is like? So, but if I want to turn to some vector looks, yeah, I want to plot as a vector field in terms of magnitude and directions. And how do I do that? Yeah, so if we can actually master, I promise every single session, after every single session, you always get hold of my presentation file. So if you can have any project come across of mine, you pretty much can copy my template. So I usually put something like template here. So actually you can actually just copy and paste, achieve the thing you want. For instance, we are not just having wing directions here, but we actually have a wing vector in terms of vector form. So now it's not showing anything like the angular degree anymore in my place. Now it's showing is actually going the north, south, east, west. Yeah, kind of is a vector. Yeah, y directions and x directions. And y direction is 3.2 kilometers per hour, and x direction 8.79552 kilometers per hour. This is with the magnitude inside. So in this case, I say, hey, I'm only interested in knowing the north-south wind. So it's called downwind, but here and now, where? Here and now. So so the system is showing me the current IP address residing right now. This is exactly my GPS coordinate. Plus, this is my magnitude. Yeah. This is my directions. So if I have something like that, in fact, I can actually also ask the system, say, here, now my IP address here. I want particular data on 1st of January. Yeah, it's showing me, hey, I have this particular data. In fact, actually, in this day, they have actually 12 set data, but now it's just showing value, interpolated values, like somehow between, it's showing something like that. Of course, if you want to see something like more details, let me see whether it will come out into something called normal. Then hopefully, coming up here, let me see value, please. It's hard to expose the entire data inside. It's not able to see value list. What's that? Okay, I try to, once I find out what's the syntax, I'll put in this template. So I send to you so you know what to do with that. Now let's say I want to plot a data wing direction as a vector field, yeah, accordingly. So in this case, the whole thing is I'm using same thing, the wing vector data, geo position right now. Of course, I can use by the same command I'm using just now called here. Assuming I don't want it to be here, I wanted some things like it become a range. You see, this now the geo position, right? I can put in my current IP address or put it here, but I say no, I don't want it to be exactly here. I want to be actually over an area where I check out Google Sheet, Google Map. Yeah, Google Map is say that from 101 to 101.4 to 102.4 and latitude 3 to 4. Actually, this is an area covering the Klang Valley. Yeah, they say, hey, okay, please give me data, wing vector data, not wing direction data, wing vector data, covering this particular area. Yeah. So the whole thing is right now retrieving right now. You see, actually, not all data are available. In certain somehow, you see, it depends how faithfully some authority are submitting data to the body they are controlling this data where Wolfram is retrieving from. But the good thing is, that's why a lot of people are using Wolfram Mathematica for data wrangling or data analytics. Even though they are missing data here, but the system actually able to omit some of the missing data. You do not have to go inside to clearly, deliberately tell which data point to omit or to take it out in order to run. The system do know sometimes not all data sets are normalized properly. So actually they have a way to do it semantically, also in a way that help you clean up quite automatically. So in this a user-defined variable called data win2 be assigned with a GPS coordinate plus a magnitude. So even though there's some missing data there, but using Joe vector plot, you see, this whole thing, same thing, is a vector plot, but I put in front simply called Joe. Yeah. So this is one building function that handle the XY vector, the element X and Y as a GPS coordinate. Yeah. Plus the magnitude behind. Whatever magnitude behind, you actually use it as a combined with the XY coordinate into the GPS coordinate, show up graphically what is happening on a certain area. So this is one strip area in Glen Valley, showing you right now, these are wind directions what's happening right now in terms of direction and magnitudes. Of course, you can put in some other legends and whatever things and label if you want to, but let's say I want to further actually to visualize the whole thing. So let's say in this case, now I say I want to make it to know where this particular strip, where does it come from? Yeah, the system right now is running now. You see, it was a small thing. Yeah, it's not looking very nice, but just showing you a concept. How does it look like? If one small strip here is very condensed. Yeah, small area. If I make it further bigger, you will show the vector field inside. I think the vector points I'm using is not actually just fitting in nicely. So now actually we're taking from Malaysia, the geographic range is only Malaysia. I don't want anything else. Of course, the geographic range, you can define the boundary, something like the region that we define, where's the vector plot so for. So geo range actually is a way actually which domain is subject to. You don't subject to a boundary of defined as a map of Malaysia. So it graphically does not come out too nicely yet, but not to worry. Let's go to the next step. For instance, if you can know this thing and can conveniently turn using the vectors and plotting the vector field like that, there's a lot of curated data actually in Mathematica. Like I say, it's like 50, 60 different libraries, a different domain, but not all of them actually organized in a vector way. So in this case here, if some of the data is not organized in a vector way, yeah, in vector form, so we can actually easily convert by using sine and cosine conventions. So in this case, I say, hey, I want to get wind direction. Yeah, wind direction, actually, it does not showing me that in a way, in a vector format. But I say, please organize in a cos and sine. Yeah, meaning that this whole weather data I'm getting right now. I say, hey, please actually, you help me to do actually. Let me see. Let me try and run it. Then you can see better how it looks like. So there's not a lot of data there. It's not organized in a way in the format of vector where Wolfram can understand. So you simply using this function that I create, you actually can replicate it for all different purposes. So now it's downloading the data right now, wind direction. It take a while to run it. It looks something like that. Yeah, it looks like today it's quite nice. Most of the data available except that 4 coordinates actually have 4 or 5. Let me see. Only 8 coordinates are missing actually data, but no issue. If I have this thing available, now the next thing what we have to do is, again, I can use string plot. In this case, because it's raw data, yeah, I need to use list string plot, or I can use list vector plots up to me. Yeah, so the list string plot, it looks like that. The data win03 is currently that's happening right now if this particular coordinate, which is same as what we did previously in Glen Valley. But let's say I want to do a polygon. This polygon called Malaysia, country data. Again, I take this another set of data called country data. I want to superimpose it. So superimpose graphic actually in Wolfram Mathematica is simply called show. Showing 2 things at the same time. Showing this list string plot and the country map same time. So now if I run this thing, the whole thing actually run again. I also have saved the data previously and superimpose it. It will come out quickly. But just show for just make sure that I just want to make sure that you can copy and paste it syntax for different purpose. So I do not want to actually refer to previous output. I just assume that we are doing all over again. I'm taking data all over again, the wind direction from this particular coordinate, this particular area. Yeah, so you're taking in a lot of data points running it right now. Once it's done, actually, it'll show you how the output look like. Let me see. Well, it's still running. It might take some time, but let me see. Fortunately, I do save it previously this morning before I do it. let me see. Here we go. Now, this is how it looks like. Yeah. This is the ring data patterns about 7 o'clock this morning. Yeah, which I did it. Now it's still running. After it running, it might come out differently. It's not like that. Now, you see, this one come out very nicely. So next thing, if I say, hey, I can do this for the wing, how about other things? So there are a couple of examples. Like these two things. One thing is, for instance, let me show you one example here quickly so we can close it for the day. For instance, I just want to get a GPS coordinate right now. This is another approach, but the entire concept is the same. Now, if I want to get a GPS coordinate in a way such that it will be like 8 by 11, yeah, 8 by 11 into the matrix 8 by 11, meaning that this latitude is from 0 to 7 and step up with 1, yeah, it'll be 8 rows. And the columns here is, I say, from 100 to 120, step by 2. So it's altogether 8 by 11, give me total points, 88 different GPS coordinates. So if I say this particular 88 GPS coordinate cover the area that I want, so next thing is, for instance, inside Wolfram Mathematica, we have another knowledge-based engine called geomagnetic model. It shows a particular point on Earth, yeah, what will be the magnetic field like. Yeah, I'm not sure. Maybe some people will like do some sort of research about magnetic field in Malaysia for some reason. Yeah. So, and for instance, people do believe that maybe the entire global warming do actually slow down the Earth rotation, which affect the magnetic field, so something like that. Yeah. So in this case here, I say I put in my coordinate 88 points, which is 8 by 11, and into this showing me what's a geometric model data. So when I run this thing, I say, hey, I want to show something called declination. I don't even know what it is. Declination is one of the magnitude of this particular coordinate in terms of magnetic field. Declination is the way to measure the magnetic field in a particular location. Say, give me the magnitudes in terms of this declination. So if I transpose it accordingly, I transpose it accordingly into a vector field accordingly, that's running right now. So because it's trying to pull up 88 GPS point, all with slightly different magnetic fields, yeah, accordingly. So not all the magnetic field come out, yeah. So the next thing is, if I want to deploy it, it's very simple. Yeah, it is say Geostream block, yeah, and because we have GPS coordinate already, the system knows where it is right now. I only have to tell the system that what kind of map I should use. There's a map called relief map, yeah. It's somehow called relief map. I'm not sure why, yeah, but it looks very nice to me. So I use the relief map. So now it comes out like this. This is magnetic fields, yeah, covering this whole area, 8 by 11, yeah, 8 by 11. You count all the 8 by 11 vectors now showing here. Of course, I do not ask to plot the system with different colors and legends, so you're not able to tell in terms of color differentiate the magnitudes. But let's see the next thing. Exactly the same approach. Yeah, exactly the same approach. Now I'm using my coordinate. I do not change it. Same thing. This 8 by 11. But I want to show what's the gravitational force actually is happening here. So now, again, ask the system to give me the output of gravitational force of this 88 GPS coordinate. Now, same thing is showing it like this. So now the next thing is a very simple deployment. If you have seen some of the video we played previously, and you can see actually this thing could be easily deployed to a website, mobile device, and whole thing can turn to cloud very easily. So this is how the gravitational force directions block looks like. Yeah. So both are using the same graphic map. Of course, like I say, if you use manipulation, in fact, you can superimpose both these maps together with different tab to show accordingly. So today, I'll touch more on vectors. I hope next month we will touch more on how to do optimization multivariate